Hello, this is the review of the Chapter 8 reading on One-Way ANOVA, effect sizes, and confidence intervals. You should use a one-way independent ANOVA when you're comparing 3 or more sample means that come from different groups. The one-way ANOVA is going to give you something called an Omnibus F value, and you'll be able to find the Omnibus F value's p-value, and the two of those together will indicate if any one or more of the sample means deviates from any of the other sample means more than would be expected by sampling error. If you get a compelling p-value, then you're going to have to do a post hoc test to determine which sample means are different from each other. So I'm going to say this one more time because this is an important point. You're going to get an Omnibus F value, and that's going to tell you the degree to which any of the sample means deviates from any of the other sample means more than would be expected by sampling error. So if you get a small p-value, that means that at least one of the sample means is deviating more than expected from at least one of the other sample means. Now, it could be more than one comparison that's different, but if you get a small p-value for the Omnibus F, that means at least one is different. There may be more, and you're going to have to do post hoc tests to identify exactly which of the comparisons are deviating more than would be expected by sampling error. Of course, I'll talk about this more when we get there in this example. Now, the logic of an ANOVA is very different from the logic of a t-test. ANOVA stands for Analysis of Variance. So that's an abbreviation, Analysis AN of O and Variance VA. ANOVA is, as it says, analyzing variance. What it's doing is it's partitioning the total amount of variance that you observe in the data and really categorizing it into 3 different groups. The variability that we're most interested in is the treatment effect variability. That's the variability that's created by the fact that you gave different groups of people different treatments. The other 2 types of variability collectively could be called error variance. Part of error variance is measurement error. You're always going to have measurement error. You can never measure something perfectly every time. So there always will be error variance created because of measurement error. Error variance is also created by individual differences. People are different from each other, and so they're likely to have different scores because they have different value, they have different traits, different things that are being measured. Again, go way back to the example that we gave very, very early in this semester. If you're measuring an infant's head, a bunch of different infants' heads, if you're doing that, it's hard to do. Sometimes you may make a mistake when you're measuring a given head for whatever reason. The procedure isn't quite right and you're off by a little bit. That would be measurement error. Of course, if you're another source of variance is the fact that infants' heads actually vary in size. So within the context of ANOVA, variability due to individual differences and measurement error are considered error variance, because what we're really interested in is the variability created by the treatment. This next slide, I think, will make this more clear. So ANOVA is going to yield something called an F value. And as I'll describe down here at the bottom, if the null hypothesis is true, you expect to get an F value close to 1. Now, here, let me pull out my pointer here. So here at this F value equation, we have the variability between treatment conditions divided by the variability within treatment conditions. That's how literally you compute the F value. Now, conceptually, you have to realize that there are three different things that are contributing to the size of the variability between treatments up here. There is the treatment effect, the fact that the different groups are getting different amounts of or different kinds of treatment, right? So if you have three groups, group 1's getting treatment A, group 2 is getting treatment B, and group 3 is getting treatment C, and so on. So part of the variability between treatments is the fact, between the different conditions, is the fact that the groups are getting different treatments. That's the variability that we're interested in. We want to know how large is the difference between the groups, because we want to know how more or less effective one treatment is than another. But in these different groups, we have different people. So these groups probably differ just because of individual differences. These three groups aren't probably exactly like each other because of individual differences. So some of the between group variability up here is created by individual differences, just like some of it is created by the treatment effect, the fact that different treatments may be more or less effective. And of course, some of the variability in this between treatment condition is also created by measurement error, because there's always measurement error. We can't measure something perfectly. Well, the logic of the F test is that the within group variability is made up of individual differences and measurement error. The people within a group are also different. So that variability within a condition is a measurement of individual differences. And then, of course, we always have measurement error. The assumption of the ANOVA logic is the amount of individual differences and measurement error in the numerator is the same as the amount of individual differences and measurement error in the denominator. So they will cancel each other out. This final F equation will help us understand it. Now, this is the actual equation. These are just conceptual representations of that. Obviously, an ampersand is not a mathematical function. So this is really just giving you the notion that these three things contribute to the size of the number that is this numerator, and these two things contribute to the size of the number that is this denominator. This last equation is really an extension of this first one, and it's a specific scenario. If the null is true, the treatments are equally effective. So that means none of the numerator variability would be created by treatment effect. So that's essentially a 0. And then what you're left with is individual differences and error over individual differences and error. And that means whatever this number denominator is, you're dividing it into the numerator, and you're going to get 1, because they should be the same number. Again, because the assumption is there's just as much individual differences across conditions as there is within conditions, and there's just as much measurement error across conditions as there is within conditions. And so they'll cancel out. If the null hypothesis is true, you should get an F value of 1. However, if the treatment is effective, there will be some variability created by these different treatments, and so the F value will be substantially larger than 1. And then, of course, the larger the F value is, the smaller your P value will be, and the more compelling evidence you will have against the null hypothesis, which is that all three treatment conditions are equal to each other. Now it's time for an example. In this example, we're going to use, or in this scenario, we're going to use the idea of studying how social media use is associated with sleep duration. Is there an association? And we're going to be doing an experiment where you are randomly assigning people to one of three conditions, and in other words, one of three levels of the independent variable. The first level is people are not supposed to use any social media for 1 week. The next level is they're supposed to use social media for only 30 minutes a day. And the third level of the independent variable is they're only supposed to use social media for 3 hours a day. Now, to monitor their use, you would put an app on their phones and computers to measure how much they're actually using social media. The dependent variable is the amount of time they sleep each night in hours, and you're recording that using smartwatches. That's your dependent variable. Of course, besides designing your study, you also need to decide on a sample size. This chapter is, of course, on ANOVA, so you're going to have slightly different requirements for sample size. The more groups you have, the larger the sample size you need. And these numbers represent the number of participants you'll need in each condition. So as the number of groups that you're trying to analyze goes up, the number of people you're going to need will also go up. Okay, so in this case, you are interested in a minimum effect size of a medium effect. So this would be a case where you're using statistical sensitivity. You have an idea of the minimum effect that you'd like to detect, and you're saying it's medium. This is different than statistical power, where you, based on the literature, you're looking for a certain size of effect based on someone else's research. This is a case where you're just saying, I am just interested in a medium or larger effect. So in this case, you would be interested in statistical sensitivity. And based on the chart here, we have 3 groups, a medium effect, and the smaller number is sensitivity. So we could get by with approximately 30 people per group. Since we have 3 groups, that would be a total of 90 participants. But of course, if you could get more than that, that's fine. I mean, that's great. Generally speaking, as long as you can afford it, the larger your sample size, the better. In this case, we ended up with 63 people per condition, so that puts us well above what is the minimum required to detect a medium effect, and that's great. Again, generally you want to have a larger sample size, as large as you can get within the constraints of your time and money resources. Now we're ready to go ahead and start doing the tests. The first pillar that we're going to be looking at, of course, is hypothesis testing with a continuous p-value. And the first step is to choose the correct test statistic. In this case, of course, you're comparing 3 sample means from different people. So that means that an independent one-way ANOVA is the choice. And specifically in this example, you're comparing the mean number of hours slept for those in the 3 different social media use conditions: the people who aren't using it at all for a week, people who are using it for 30 minutes a day for a week, and people who are using it for 3 hours a day for that week. The second step, of course, is to assess the statistical assumptions, and these are the same statistical assumptions we've been dealing with all semester. Data independence, of course, you want to make sure that people, one person's sleep times aren't influenced by another. So you probably wouldn't want to use people who, like married couple or something. 2 people who are sleeping perhaps in the same bed, if one person is got randomly assigned to a condition where they're using a lot of social media use, and maybe they're staying awake a lot now, surfing the net or doing things on social media, while the other person is trying to sleep, obviously that would interfere with the other person's sleep time. So that would obviously not be appropriate. These type of situation you'd want to control such that each person in this study is sleeping alone while the study is going on, so that someone else isn't influencing them. The next one is appropriate measurement of the IV and the DV. The independent variable defines how the 3 groups are different. In this case, we have 3 levels of the independent variable: no use, 30 minutes of use, and 3 hours of use per day. So that's the 3 levels of the independent variable and how it's defined, so that's great. The dependent variable here is, again, a ratio scale of measurement because it's the number of hours they slept. Of course, you can't have less than 0 hours, so this is a ratio scale of measurement. So yeah, this is just fine. Normality assumption is the central limit theorem again. In this case, we have a sample size of 63, so we would expect the distribution of sample means to be normal, just because the number of people in each condition is so high. But we would also get a normal distribution of the distribution of sample mean differences if the original population had a normal shape, and that's likely the case here as well. The final assumption is the homogeneity of variance assumption, where the three conditions have similar variances or similar standard deviations in the populations from which they're drawn. And that's likely to be the case here. There are some tests that you can use to test this using a computer, but you can also use the rule of thumb. We'll just look at the standard deviations of the three groups, and if they're not, if one's not 3 times the other, we're probably just fine with this. The next step is to identify the statistical null hypothesis. In this case, we're saying that all 3 sample means are going to be equal to each other if the null is true. Another way of saying that is that the between group variability, again, the variability created by the treatment effect, the individual differences, and measurement error, that number that is generated by combining all of the variability by individual differences, measurement error, and the treatment effect, that number is about the same as the within group variability, which is just individual differences and measurement error. Again, we're basically saying that the treatment is creating no variability. And that's what's reflected here with this conceptual F equation. Notice the amount of variability created by the treatment is presumed to be 0, and if that's the case, you will get an F value of 1. If the amount of variability created by the treatment is greater than 0, then you're going to get an F that's greater than 1, and if it's quite a bit larger than 1, you're going to get a small p-value, which will tell you that you have compelling evidence that the treatment, that one of the treatments, at least one of the treatments, is better than at least one of the others. Again, if the null is true, you expect to get an F value close to 1. If you get something far from 1, you're going to get a small p-value, and that's going to be evidence that the null hypothesis is probably not true, and that at least one of the treatment conditions is more effective or different than at least one of the others. The next step is to graph the data from each individual condition. What we can see here is the group that used no social media for a week had the highest sleep average. Light was a little bit less. Light use was a little bit less, and then the heavy use seems like it was quite a bit less. And once you get used to reading these confidence intervals around the means, you'll be able to anticipate the results. There's quite a bit of overlap between these confidence intervals between the no use and light use. So I'm suggesting that this is going to probably be a pretty high p-value here because there's quite a bit of overlap. However, when you're comparing the no use to the heavy use, there's no overlap at all. So that's going to give you a pretty small p-value. Also, the difference between the light use and the heavy use, there's no overlap. So that's going to give you a pretty small p-value. If you get used to reading these, you could, again, anticipate the results that you're going to get. I would expect that there's probably, this difference is probably going to be due to sampling error. It's not large enough to offer compelling evidence that there's a difference between no use and light use. The difference between no use and heavy use that's going to be compelling because there's no overlap. And the difference between these two is probably going to be compelling. So we'll get a small p-value between this comparison and a small p-value for that comparison, probably, once we have to do post hoc tests. Now, how do we get the Omnibus F? Well, we have to get an Omnibus F first to decide whether or not we have to do post hoc tests. Now, I'm not going to go into the details of how you compute the F by hand, The formulas is here, and it's conceptually exactly what I described above. You're taking the variability between treatments, and you're dividing that by the variability within treatments, and then you're going to come up with one F value. Again, if that F value comes up to be substantially greater than 1, then you have compelling evidence that there's a difference somewhere. Here we crunch the numbers down here, and we're going to find that the Omnibus F value is a P of 0.00016, very small. So that means at least one of these comparisons, one of these differences that we talked about over here, is compelling. Now we have to go and find which one by doing post hoc tests. Now if you use logic, the biggest one is going to be the most compelling p-value because it's the biggest difference. So we already know that the biggest difference is compelling. What we don't know is the anything involving this middle number, this middle mean. Is this going to be compellingly different? Is this comparison going to be compellingly different? Now, I've already indicated what I expect based on the graph, but we have to get the numbers because we're going to have to report the specific statistics rather than just making an eyeball judgment. Again, to summarize here, if you're interested in actually computing this, it goes over that in the reading, and you can do that. But in this class, I'm not going to require you to crunch the ANOVA by hand as much as know what all the numbers mean and how to interpret them. Here are the numbers down here. This is the variability created by the treatment and everything, individual differences of measurement error. And this is the variability created by all the different individual differences of measurement error. And now you have to convert those by averaging them based on the number of things contributing, right? There's only 3 groups versus down here there's a whole bunch of people. So you have to divide those things out and then divide out these mean squares, you get the F, and then here's the P. All right, so now we need to interpret that p-value. And just like in previous chapters, the probability of getting the obtained F value of 9.16 or something further from 0 or further from 1, I guess it's the same thing, that is very, very small. It's going to happen very, very rarely would you get an F value of 0.9 if the null hypothesis is true and there's no differences among the 3 groups. You're also assuming that there's no methodological flaws in the study. So again, based on this F and P value, at least one of the groups deviates more than would be expected by chance or expected by sampling error. Now there could be more than one difference in there that deviates more than sampling error would expect, but there's at least one. And so now we need to do these post hoc tests to determine which groups are different from each other more than would be expected by sampling error. Now you have a lot of different choices. This slide certainly does not represent all of the different post hoc tests that you would have available to you. It does represent 3 common ones: Fisher's LSD, Tukey, and the Games New Howell. Those are 3 commonly used post hoc tests, and this chart represents how they're different from each other. The first major difference is the fact that Fisher's LSD does not do anything to correct for multiple comparisons, whereas the other 2 do. Now, what does that mean? The more comparisons you make, the more chance, the higher the probability is that you will have an error in that you will find a difference, you will find a small p-value just due to sampling error. Again, you can get a small p-value just due to sampling error, and the more tests you do, the more likely it is that at least one of them will get a small p-value just due to sampling error. So a lot of statisticians, a lot of follow-up tests, post hoc tests, try to correct for that potentiality by giving an adjustment to the p-value for a post hoc test. The LSD does not do that, and the logic behind not correcting for it is generally people try to use only the LSD when they're making a very small number of comparisons, and this, basically 3 groups. If you just have 3 groups, you're just making 3 comparisons, group 1 to group 2, group 1 to group 3, and then group 2 to group 3. So that's just 3 comparisons. If you're making a small number of comparisons, it's less important to correct for the multiple comparisons because there's just not very many of them. However, in some studies, if you do have 4 groups or 5 groups, the number of comparisons you're making goes up more than just 1 by adding a group. It goes up it goes up quite a bit. If you have just 4 groups, you're comparing 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. So that was quite a few number of comparisons just with 4 groups. So if you have 4 groups, it's common to make some kind of correction for the fact that you might be getting a small p-value just because you're making multiple and multiple comparisons. Both Tukey and Games Howell do that. The only thing that makes these two different from each other is that Tukey assumes homogeneity variance, excuse me, and the Games Howell does not. To summarize this, if you're doing post hoc tests, a Fisher's LSD is always going to give you a smaller p-value than, say, a Tukey is or a Games Howell. These will give you, because it's not making a correction for multiple comparisons. The corrections that these two make, is by increasing the p-value. Now, of course, that's going to change your interpretation, because a larger p-value means you're going to have less compelling evidence for a difference. These are more conservative. They're less likely to find compelling evidence of an effect. And a Fisher LSD is more likely to find compelling evidence of an effect. And you should just know this when you're choosing them and when you're reading research. Now, because we're, in this case, just having 3 groups, we just have 3 comparisons, we can get by with using Fisher's LSD. So the first comparison, we're going to find the mean difference between those who use no social media for a week versus those who use light. They differed by 0.2 of an hour in sleep per night. And we do a Tukey LSD t-test. This is just like a t-test that you've done before. It's using a slightly different denominator, but than some of the other t-tests. But basically, it's just doing a t-test to determine the probability that this difference could occur due to sampling error. And you get a p-value of 0.29, which is not compelling evidence. So there's no compelling evidence that there is a meaningful difference in sleep between those who have no use for a week versus have light social media use for a week. This is not compelling evidence. Then we're going to compare the no use group to the heavy use group. They differed by 0.8 of an hour, and that was a very compelling difference. That's very unlikely to be due to sampling error. Then we compare the light use and the heavy use. They differed by about 0.6 of an hour per night. And again, that is also compelling evidence. So what we have here is compelling evidence that no use and light use, there's no compelling evidence of a difference there. We do have compelling evidence for the idea that heavy use leads to less sleep than no use, and we have compelling evidence that heavy use leads to less sleep than light use. And here's where we're basically interpreting that again. No compelling evidence for an effect between no and light social media use, again, because the p-value was fairly large. Basically, we're saying this comparison is not compelling. Again, we anticipated that. that because this overlap between the confidence intervals is so great. Then we're comparing the evidence for heavy, we do have compelling evidence for heavy use for social media use, leading to less sleep than no use, comparing these two means. Again, we have a very small p-value because, again, there's no overlap between the conditions. And then we're comparing the middle light use to the heavy use. And again, no overlap and still very compelling evidence. So heavy use seems to have a very detrimental effect on the amount of sleep that you have in a given night. Now we're ready to move on to the second pillar, which is practical importance with an effect size. Now, when you're doing ANOVA, you have a number of different effect sizes. First, we have the overall effect size for the Omnibus Effect. In other words, we want to represent overall how much of an effect does social media use have on sleep. And we have a number of options here. We can use partial eta squared or we can use omega squared. They're similar. Generally, omega squared is going to be smaller, and it's also considered to be a little bit more accurate. The partial eta squared will tend to overestimate the effect, and so when possible, you want to use the omega squared. Again, we'll be doing our analyses using computer, and so you're limited to what your computer program does for you. A lot of programs like JASP and Jamovi will provide omega squared for you. If you're using SPSS, you'll be limited to using partial eta squared. But if you have a choice, I would recommend using omega squared because it's going to be a more accurate estimate. Here are the guidelines for interpreting both partial eta squared and omega squared. In this case, 0.08 is between medium and large, so this is a medium-large effect. We can conclude from this that overall, social media use has a medium to large effect on the amount of sleep people get in a given evening. Now, we're not quite done with examining effect size yet because the overall effect, while it can be useful in summarizing the relationship between two variables, getting into the detailed comparisons between specific levels of the independent variable is also very important, and frequently that's more critical to examining the relationship between the variables in a more detailed way. So in this case, we're going to compute a Cohen's d. This is a similar Cohen's d that we've done in previous chapters. It's using a different measure for the denominator, but it's interpreted in a very similar way. So we find the difference between the two conditions, which is at 0.2 hours, and then we're dividing that by the denominator, of course, and then we get an effect of 0.19, which is a small effect. Again, something close to 0.2 is small, something close to 0.8 is large, something close to 0.5 is medium. So we can see that the three comparisons that we have here, we have one of each. We have no use, light use was a small effect. Again, previously we found that this difference was could very well have been due to sampling error. Didn't have no compelling evidence that this is not sampling error. And then we have no use and heavy use. That is considered a large effect. And then we have light use and heavy use, and that's considered a medium effect. So we'll want to consider this when we write up our results eventually. The third pillar is estimating confidence intervals, estimating population parameters with confidence intervals. And again, we won't go into how these are computed. I'm more interested in your ability to interpret them. So we take the point estimate, which is just the mean difference that we observed in the previous slide, and then we have a lower bound by subtracting the margin of error from that point estimate. Then we have an upper bound by adding the margin of error to that. Again, the book will go over how these are computed if you're interested in that, but we're going to be more focused on you interpreting these. So this means, again, that for the no use versus light use comparison, the difference might be as much as close to 0.7 hours per evening, but it might be as low as a quarter of an hour in the opposite direction, in that the light use sleeps more than the no use. So this, again, there's a wide range, and you're not finding very compelling evidence here of an effect. Now, comparing no to heavy use, the point estimate is 0.8 of an hour, but it could be as high as 1.3 of an hour to as little as 0.3 of an hour. So again, even the lowest probability is about a third of an hour more sleep, but it could be as high as 1.3 hours more sleep for people who don't use social media compared to those who use it heavily. Quite a wide range. It's something to consider when you interpret your results. Then we can have a similar conclusion when it comes to light versus heavy. Our best guess at the population parameter is something close to 0.6, but if we had a lot of sampling error, it could be as low as 0.13 or as high as a full hour. But again, the point estimates are our best guess, but we need to recognize that we could be a bit off on the high or low side, and that's what these boundaries give us. They give us a range of plausible values for the population parameter. Again, this is our best guess, but if we had a lot of sampling error, it could be way down here or it could be way up here for each of these parameters. As always, we need to consider the research methodology. Were there any problems with the study that we need to consider? Well, again, this study had a lot of good characteristics. We randomly assigned people to conditions, so we actually did an experiment. We had good measurement of the dependent variable by using smartwatches. Now, maybe those smartwatches aren't a great measure of the dependent variable. We might do better if we actually hooked people up to EEG and measured their actually sleep waves, but maybe that was a little too expensive to do. So this was maybe the best we could do at the time. We used apps to monitor their actual social media use by putting those on their computers, and so we would check to see that they didn't use more than their allotted time on their phones or computers by using the apps. Of course, people could still have cheated, maybe by using someone else's phone or someone else's computer to check things. That would be a potential confound that we would, that could have happened. We don't know that it happened, but it's possible. But overall, this methodology looks fairly strong. There's no serious problems here that would cause us to doubt the results in any serious way. Of course, we need to consider the scientific literature. How do our results relate to other research in the area? Maybe there isn't previous research in this area. Maybe there is. You would want to consider it if there is some. You also want to offer your interpretation of the results. What's the implication? Where should someone go with this? What would be the result of this? Okay, there's a lot to write here. You have a lot of things to talk about. You need to talk about the overall F, the Omnibus F, and you also need to talk about the follow-ups. And then you need to talk about, of course, all of these different six components of a solid answer. And I'm going to walk through them. In some of the previous examples of this at the end, when we write up our scientific conclusions, it's a little easier to tease out where each of these six components are. But when there's this many things going on, often they get merged into a single sentence. So it's a little harder to piece out where each of these different things are. But I assure you, each of these different things are here, and I have tried to color code them to the best of my ability. So first we want to say what we compared and how. So you ran an independent ANOVA, and you were comparing the sleep time in 3 social media use conditions, and you'd say what they were. People had no use, light use, and heavy use. So you say what you were comparing and how you compared it. Then you need to talk about the statistics and provide them in APA format, so you know that F is the symbol for ANOVA. You have two different values for the degrees of freedom. The first one is the number of groups you had minus 1, so that's 2. The next one is the number of people you had in the study minus the number of groups. So you had 63 people per group, and then so you multiply 63 times 3, and then you would subtract from that the number of groups, which was 3, and that's how you would get 186. Here's your obtained F. Here's the p-value for the overall F. Here's the omega squared, the mean square error, and then you're going to refer to a table. There's so much information to convey when you do ANOVAs. It's usually helpful to present the means and standard deviations of each condition in a table, and that's what I'm referring to here. The means and standard deviations of each condition are in table 1. So here we would have table 1. Now it's time, because you have compelling evidence that there's a difference between the groups in terms of the amount of sleep that they had. Now you want to go on and start talking about the post hoc tests, and that's what this next paragraph is going to do. The mean differences, Fisher LSD, p-values, Ds, and mean differences for the CIs are in table 2. Again, there's a lot of statistics to report here. And so I'm referring them to these statistics, and I'm telling them what I did. Of course, I could have run many different types of post hoc tests, so I need to tell them which type of post hoc test I did actually run. And that's what I did in this sentence here. Now I need to describe those statistics and provide some analysis of them. I need to talk about them a little bit. So the Fisher's LSD post hoc tests revealed that the heavy social media use group slept 0.8 hours or 48 minutes less than the no social media use group. This difference was large, I'm interpreting the effect size, and it's very unlikely due to sampling error, interpreting the p-value. The heavy social media use group also slept about 0.6 hours or 35 minutes less than the light social media group. This difference was medium, interpreting the effect size, and unlikely due to sampling error, interpreting the p-value. Finally, the no social media use and light social media use difference in sleep was small, interpreting the effect size, telling you what it is. The mean difference of 0.2 hours with 12 minutes, and may have been due to sampling error, again, because that p-value was not compelling right there, right? Notice how all this information is in the table. So I don't need to put it all in the paragraph. Just pick out the key points that you want to focus people on. But there's other important things that aren't written up that they can go refer to and find if they need to. Next, I want to talk about the confidence intervals. The 95% confidence intervals suggest the differences in sleep time between no social media use and heavy social media use could be between half an hour to 1.3 hours of sleep per night. While this is a wide range, the lowest plausible population parameter likely has practical importance. If you think about it, a half hour more or less sleep a night, for most of us, that could make a very large impact on our lives. Now, when I talked about the confidence interval, I really just talked about one of them. I focused on the confidence interval of the biggest difference, the comparison that had the biggest difference, to really highlight the importance of the relationship between the amount of social media use and sleep. A person could go ahead and talk about all of the different 3 comparisons and their confidence intervals, but I think in this case it would be a little bit of an overkill. We've provided the values for them so that they can interpret them for themselves, and I'm interpreting one of them for them so the way that I think about it. And so they can apply that logic to the numbers that they see there as well, and make their own judgments. But having at least something here, I think, is a good idea. Finally, we want to talk about the methodology and the literature to the extent that we're able. These results are consistent with the previous literature, showing that greater social media use is associated with less sleep. Because this study was a true experiment, it allows us to determine that social media use caused participants to sleep less. One possible methodological concern with this study is that we don't know if people really use social media for the amount of time they were supposed to. We may also be concerned about the accuracy of the sleep times. However, these results are promising and certainly suggest that future research is needed in this area. Future studies should also use larger sample sizes because there is a great deal of variability in sleep. Now, I've said quite a bit of information there. Let's break it down just a little bit. I'm referring to the previous literature saying that this is consistent. I'm commenting on a strength of the methodology, that this was used a true experiment by randomly assigning people to conditions. That's an absolute great strength of the study. I'm mentioning some limitations, that maybe people cheated. It's possible that they cheated, and I'm mentioning that as a possibility. And I'm also mentioning that a weakness might be that we could possibly measure actual sleep times more accurately. It's always a good idea to mention your limitations. Now, none of these are serious limitations. Nothing that would qualify my interpretation of the results. The methodology is certainly sound enough to support a solid conclusion here.